First time doing this. Okay, I'll do this for the recording. This is Space Enterprise at Berkeley. It's Ignition 2, the Propulsion Ignition session. So what is propulsion? The goal of propulsion overall at a high level is to get the fuels from the propellant tanks into our engine at the right flow rates, which is the amount of fuel per second, at the right pressures, which is like how hard the fuel is flowing into the engine, I guess, at the right temperature, at the right, like all conditions. So that's kind of like the high level, very high level overview of propulsion. And we also do engine design. So we design our engines to operate to get us to our altitude goals, whether that's 45,000 feet, 15,000 feet, or getting to space. So propulsion does a lot of things in a lot of different areas. We do a lot of chemistry to figure out engine things, engine cooling, engine performance. So maybe Rustam would be familiar with that. He does chemical engineering. We do a lot of plumbing, which means like putting together a bunch of pipes to get the fuels where they need to go. Nolan and William are resident experts on that. They know a lot about how fluids behave in pipes, how they behave in different scenarios. There's a lot of safety concerns, right? We're dealing with a lot of explosive things. We're dealing with propane, we're dealing with liquid oxygen. These are pretty dangerous overall. So Maddie is our chief safety officer. She knows a lot about the operating procedures when dealing with those. So those are kind of our experts on things. And then we all come together, use that information, design our system to get the fuels where they need to go, integrate that system and fly it. So among that, there's a lot of other things going on, right? It's not just about the fittings, it's about the aerostructure that holds everything together. It's about the avionics that read all of the sensors and combine that information. It's about the simulations team that starts off by designing the engine, starts off by giving the propulsion team the parameters we need to design into our system. It's about going back to the simulations and figuring out, oh, how are simulations inaccurate? How can we update those simulations based on actual testing and move those simulations forward to better inform how our engine can be improved in the future, how our rocket can be improved in the future. So it's all tied together on some level or another, kind of starting from simulation way at the bottom, then like propulsion and avionic structures on the next level, and then flight on the top. So yeah. So as I said, process begins in simulations. So we start with those high level parameters. We always have a goal with the rocket team. Like usually you're not going to say, oh, let me build a rocket with this much thrust, this size, blah, blah, blah. You always say, let's get a rocket to space, right? That's 100 kilometers. Then you take that massive system goal and you start breaking it down, right? As a school, we only have access to certain materials. We can't maybe machine like these crazy aerospace grade materials. They just cost too much. You have to kind of narrow that down. We say, let's use like basic aluminum, stainless steel. Let's set those aside as our materials. Let's say we can only get certain fuels, right? Like it's kind of hard for us to get like rocket propellant, but maybe we can substitute that with jet fuel, which is almost as good as like RP1, which is rocket propellant one, which is like really refined kerosene or petroleum. We have other limitations, like maybe IPA is easier, like it's just isopropyl alcohol. We can buy that online. If it spills, it's not a big deal like it would be with oil. Things like that. So that massive high level overview of let's start out by getting to space boils down into a few different decisions that are limited by the limitations of our club. And that starts the first order calculation. So a lot of that work is going into E3, which is our space shot rocket right now. So Nolan's using a lot of that information to work with the simulations team, work with the propulsion team, work with the structures team to figure out how all of those like high level goals get boiled down into actual engineering. Because once you've made those decisions with the simulations, once you've done those first order calculations that determine how big your airframe needs to be, how big your tanks need to be, you have to really boil that down into real engineering hardware. So Nolan is working really hard on that. You can see this is an E3 trajectory calculator. So based on kind of apogee time to apogee, our weight of everything, diameter, burn time, things like that, we can figure out an estimated velocity. We can figure out like the drag on the airframe, acceleration. We have like a massive simulation. So I'm not sure if you guys know about Simulink, but Simulink is kind of like the Mechie tool of the trade. Simulink is a very easy way to visualize very complex systems. It's like a block diagram based system. There's also a bit of programming involved in it, but this is kind of where we start. We have a simulation that is slowly built up of many, many levels of detail, and that informs our overall rocket. So you can kind of see this is one block model, but if you look really closely, there's a tiny block model in here, right? Like its block model is all the way down. And by starting with a big block, or like maybe 5 blocks that just cover like lift, or we don't deal with lift, we deal with thrust. We have thrust, we have like a drag equation, we have a mass equation. Like inside those blocks, there's thousands of tiny lines of code, tiny blocks inside of those things that all come together in these high level overview. So that's kind of where we start. We go from top designing that and slowly fill in all of those functions to inform our simulations of how they can be the most accurate. And as I said, simulations never match reality. It's always going back to the drawing board and figuring out how to adjust those simulations. So I'm sure, E1 started at 45,000 feet. That was our initial goal. As we went from 45,000 feet to actually building the rocket, it dropped down to 35,000 feet. That was the number I heard when I joined. Then a few months later, they're like, okay, 30,000 feet, that's our goal. Next few months, 25,000 feet. Finally, estimate was 15,000 feet. And then our parachute deployed too early. The parachute was slowed down a lot. It only hit 11,000 feet. So, 45,000 feet to 11,000 feet, that's a massive difference. And that's not all on simulations, right? There's a lot of things that went kind of wrong. There's a lot of things where we thought we were a lot better at making tanks really thin, even though we knew what size our tanks were. There's a lot of things about how we're stuck with the airframe we have. And we're like, oh yeah, the airframe's only going to cost or only going to weigh 10 kilograms, but then you actually weigh the airframe, it's 20 kilograms. There's a lot of things like that where you have to really go back to first principles, go back to the actual materials you'll use, plug those into the sims and make sure they line up with reality. So then once you have your simulations, the simulations team will be like, okay, we need a 17 kilonewton engine, so 17,000 newtons. I'm not sure what that's in pounds, 3,000 pounds. Yeah. Okay, so let's say we need an engine that can provide 3,000 pounds of thrust. That's like a single number, right? You can't design an engine with that knowledge. They'll say, okay, for 3,000 pounds of thrust, we need to inject liquid oxygen at 5 kilograms per second. We need to inject isopropyl alcohol at 3 kilograms per second. These are all like made up numbers. I'm sure they're in the right order of magnitude, but like, don't take any of these numbers as real. But we have to get these fuels into the engine at this mass flow rate. And that's a lot of fuel, right? Pumping like maybe a gallon jug into your engine every second, that's kind of tough. So once the simulation team says you need to get that performance into your engine, then we go back to the drawing board. We figure out our plumbing, what's going to happen. We figure out our valves, flow regulation, plumbing. So valves control the flow of material. They can open or close. Flow regulation changes the pressures of things. Plumbing just like carries the fluids around. And things aren't always perfect, right? So yeah.
The diagram there.
Yeah. Yeah, so we use a pressure fed rocket. So there's a lot of ways to get these fuels into your rocket engine. In industry, see a lot of people use turbo pumps, which are like pumps that pump the fuel into your engine. Those operate at very high pressures, very high speeds, maybe 30 to 50,000 revolutions per minute. And when you're dealing with things like liquid oxygen, those are very hard for a collegiate rocketry team to design and test. Also, things aren't aren't very efficient at our scale. At a tiny scale that we might use, you may get 30 to 40% efficiency with a pump, whereas maybe with like SpaceX rockets, they get 90+% efficiency, edging towards 100% or 99% efficiency. So some things just don't make sense at our scale. So yeah, we do use an inert gas, nitrogen, to push fuel and liquid oxygen out of our tanks and into our engine. You might see a lot of other teams or diagrams online. They'll use helium instead of nitrogen. Helium is another good choice because it's an inert gas, so it doesn't react with things. You can get higher flow rates. It's a lighter gas, so it has a lot of advantages on the fluid side of things, but it's very expensive. So filling up one nitrogen bottle for us on a Eureka 1 size rocket would cost around maybe $80. Filling one up for like the same rocket with helium would cost a couple $1,000. So that's kind of the crazy price difference between nitrogen and helium. And we've decided that the performance penalty is worth it. So what a lot of people say is use the cheaper gas when you're testing. And then when you go launch that thing and you don't think it'll get high enough, you spend the price on the expensive gas and then launch it. But that's one of the things about our team. You'll see some teams, they always use helium. They have a lot more money than us. They have a lot more resources than us. We're kind of a scrappy team using what we can get, and helium is just out of our price range. Yeah, so sorry to go off on that tangent, but hope that was helpful. Yeah, so once we have those high level parameters, we can design our subsystem. We know our fuel flow rates. That means your pipes can't be too small because then you can't put enough fuel through them. So our pipes have to be a certain size, our valves have to be a certain size, our tanks have to be a certain size, have to be able to handle a certain pressure. And once we put all of that together, we can purchase plumbing and assemble a system. So as it says on the slides, it's a cyclical process. If we're not getting the pressures we need, our 1-inch pipe isn't big enough, our pressures aren't good enough, we'll go back to the sims team, we'll say, hey, can you plug in these pressures into the simulation and see how that will be? And Nolan might say, oh, that'll take us from getting to space to only maybe 80 kilometers. Space is 100 kilometers. And we'll be like, okay, fine, let's make that pipe bigger. Then we go back, okay, we've made this pipe bigger, now it's a heavier pipe. Let's go back to Nolan, add that mass to our system. How does that get things? So, in the end, it's a very back and forth process, right? You optimize one thing and it kills efficiency in another area. So it's a tough decision. It's always a bunch of decisions that everyone's fighting for their own space on the rocket. Plumbing wants smaller plumbing, structures wants smaller plumbing, Sims wants bigger plumbing that weighs nothing. It's all this massive argument over where to draw the line or where to wiggle things around in the right direction. So it's a pretty complicated process, and it's a big back and forth that we're always trying to solve, because there's just no one way to do it. I'm sure there's a perfect way to do it. If you have like a massive neural network, you're a great programmer, you could like get it perfect. But the best way to do it for us is to actually build a rocket and test it out. So yeah, so once we have all of our high level overview, we kind of know we need a tank here, we need a tank there, we need a valve here, we need a valve there. We have to go out and procure all of that. So choosing components and designing our CAD model comes next. So we have a few different things we do. We're optimizing for cost, of course, optimizing for mass. We want everything as light as possible. We're prioritizing commercial off-the-shelf components. That's what COTS stands for. That means we don't have to spend our own time manufacturing components. Often they're a lot cheaper just because they're mass manufactured. So we're doing this optimization with every part we choose on the rocket. Like, do we make it ourselves? Do we go buy it? What do? Do we wait 3 months to figure out a sponsorship and get parts for free? You know, it's all a big decision matrix going all the way down and continuously throughout the process. So once we've chosen our parts, we lay out all the connections and we assemble those connections. We create a CAD of the parts just because CAD is the best way to deal with a system this complex. And then we assemble those components in the CAD system. So you can see here, this is one of our initial test stands. It is a cart setup. So you can see we have tanks on this cart. We have our engine right here. We have all of our avionics go in the box right here. And this is where we test. They have a really big I-beam. So it's just an I-beam because it's shaped like an eye. We mount our engine to it, and then we can test our engine. So the great thing about this is in the testing phase, it's great just because everything's very easily accessible. It's all below neck level, so it's easy to tighten fittings. It's easy to swap things out. But obviously, it'll never fly. Yeah.
Why do you have the car on wheels? I feel like that could be a safety hazard, so you're running testing a rocket engine at full power.
Yeah, so wheels, it's just so we can move it around during testing. When we're actually hot firing your engine, it's not rigidly attached to the cart. It's mounted on linear slides here, so the engine can slide back and forth, and it's bolted to our crush transfer assembly into the I-beam. So this engine is basically fully bolted through this. This is restraining the engine. It's bolted to load cells. Load cells are bolted to this plate. This plate is bolted into the I-beam. So that engine is basically firmly mounted onto the I-beam. Yeah, it's not like if the cart moves or the wheels come unlocked, the cart would start spinning. We have had test systems in the past where they haven't been mounted so well, something goes wrong, falls over and starts spinning, just because, you know, you have 4,500 pounds of pressure. If that gets out of there, it can cause a lot of havoc, be pretty dangerous. But yeah, overall, the system is pretty safe. When we're doing cold flows, which is where we blast liquid nitrogen to our system, I can talk about that a bit later. We do make sure we have concrete blocks behind the wheels and keep that rigidly attached, but those don't produce any thrust. Those are just testing things, so you know it's not much of a hazard. And if the cart does start spinning, we're always at a far enough distance when it's pressurized, so it's not a big concern. Yeah.
Also,
Yeah.
to be clear, the cart was never spinning while it was burning. Yeah.
Oh yeah. This was another tiny test stand, like very simple, not this crazy. Yeah, the spinning thing was quite different. Yeah. Yeah.
All right. Why don't we center the engine? Why is it wrong?
Oh, so it just made sense with the way it worked because you want to mount to this I-beam, so you kind of want it out to the side. And you want the pressure tank going into the propellant tank going to the engine, so it doesn't make sense to kind of straddle it because then you have lines going across the engine. Also, if that engine blows up, you want this big. This isn't fully catted, but there is a blast shield that you may see in later images that do protect the rest of the cart from damage. Just because first hot fire, we did a vertical configuration. When the engine blew up, the fire went up, everything was above it, all the tanks, all the avionics, melted everything. We couldn't get control of the system. It was a big hazard. There's all this talk about like, we have all this propellant in our tanks. The tanks are full. All our avionics are on fire. We can't open the valves. What if they blow up? How do we safe that system? So this system creates a much safer thing until we validated our engine. And then we can shift to that rocket shaped system once we know everything's good. Yeah. So this is kind of in a state of development. So we use this as a development system once we had gone vertical for other hot fires. We're currently on the system just because we're again developing the system, but we're also in parallel building up a vertical system. Yeah. Does anyone have any questions about this cart setup and why it's useful? Yeah.
The cart setup is specifically to test like the mixtures of propellant and oxidizer and for the engine, correct?
Yeah.
How do you test like the avionics?
Yeah. So this actually has all of the avionics that we do fly. So in this box back here, we have temperature sensors, pressure sensors, all hooked up to this plumbing plugged into those avionics. So those avionics may be in a different form. They may be in a different circuit board or something, but those avionics are pretty much using the same component, same code that'll eventually fly. So it is a good analog. We do test everything in this cart, or as much as we can. Yeah.
There's a lot of testing that we do, like
not by flowing to the test for avionics. You can just like see if the sensor is working without actually like.
Yeah.
It's like by the time we actually flow, it's like we have pretty good confidence in like all the avionics.
Yeah, another thing about the system is a lot is automated. So we can stand far away, run things on the cart through the avionics system. These are linear actuators. We have a mechanism to open and close valves on our system. So this cart gives us a lot of flexibility. If we need to make changes, it's easy. It's all laid out there for us to use. One thing that does change is this has a lot more piping than our vertical system, just because it's more spread out. So that causes things to change, right? Because if you have a long pipe, there's a lot more friction, which leads to pressure loss. So your pressures are different. So when you do move to the vertical system, we do have to do more tests to make sure we understand that system well. But the cart gives us a really good way to test things easily at a first test. Yeah.
Are you measuring accelerations in all these directions? So, we're in front of us, it's pretty lateral. But that's, this is what, are you measuring that, or is it just like a single axis?
Yeah, so on this setup, there's 2 load cells. The 2 load cells was just for ease of use, so you can kind of tell is the engine going left or right. But ideally, you want a 3 load cell setup. So on this cart, initially we had a 2 load cell setup. When we shifted to our vertical test stand, we shifted to a 3 load cell setup. So 3 load cells, you have like all 3 axes. You can kind of tell if your thrust vector is not symmetric about the center. We don't really have to worry too much about rotational like torquing. So we don't have like a 6-degree load cell setup, which I've seen. But we did have 3 on our vertical system, and when we do hop our cart, we are going to test a thrust vector control system. So that's where we move our engine around. So to test that, we will have a 3 load cell setup for that. Yeah.
I remember from the earlier presentation this morning that you guys said that. Do you guys have any plans to actually thrust vector control system on the Google rocket?
No. Yeah. So unfortunately, thrust vector control is where you move your engine around, and that's airing really close to like ballistic missile territory or missile territory. So the government has a lot of rules in place where we're not actually allowed to fly that. I mean, technically, we're not allowed to fly metal rockets of any size. So yeah, we're not going to fly that.
Why develop it if you can use
$15,000. There's a competition, and if we can get it working, we get $15,000. Yeah, so it's kind of like we're doing this for this competition. It's a great learning experience too, even if it never actually flies. And you know what, maybe we'll get a waiver at some point to fly it. That's not going to happen. But one thing is like to act. What? It would be. Yeah.
When you guys are seniors and we're all gone.
One of the things about thrust vector control is like we have a lot of international students on our team, and we don't want to close up access to that. And to get waivers for that, to even apply for that, it's hard to do that while still being able to accept everyone. So to make sure we don't even risk touching ITAR. And ITAR is, I'm not sure what treaty on arms and something. Okay, yeah, so that basically stops us from building anything that could turn into a missile. And that actually presents a lot of issues later. If you fly your rocket too high, GPS stops working because GPS thinks it's mounted into a missile. If you go too fast, the GPS will think it's a missile, it'll stop working. There are loopholes around that, things we're trying to find. We're trying to find GPSs made not in America because they don't have those locks. We might use a Swedish GPS, things like that. Yeah.
I know that like Russia has
Yeah.
similar.
Yeah, so a lot of so it's not actually built into the constellation, like the satellites don't know how fast you're going, it's the chip. And that chip, it's really hard to get like what they're called unlocked GPSs. Planes have them just because they go fast and high, but it's hard for a consumer, for us to get an unlocked GPS. Some teams get them by working closely with, a lot of CubeSats have them, and university teams build CubeSats, so they'll work with like a CubeSat team to get that unlocked GPS. But generally it's kind of tough. So that's something we're kind of working on. We think we found a potential candidate that might work higher than like most GPSs, but that's something we're kind of working on in the background. A lot of other people, like they use special chips that avoid doing the math that figures out how you do the speed. So technically they're legal, and then you do the math on your own chips to figure out what speed you're going and where you are. So that skirts the law. So, ITAR is something we're not really running into legally, like we don't have lawyers pounding on our door, but technically the government could come in here anytime and in theory shut down our club, but they're not going to do that. That's the problem with all of these fancy things. Yeah.
So the rocket uses the numerical methods.
No, pure fins. So we get stabilization through fins. So the way fins work is, if for anyone who doesn't really understand how they work, as the rocket, let me draw this.
Like a dart.
Yeah, so you have your rocket, you have fins here, You have a center of gravity somewhere here, and at that center of gravity, your rocket will pivot around your center of gravity. If any of you guys have taken any physics classes, like every moving part kind of pivots around the center of gravity. You have something called the center of pressure. Center of pressure is where all the aerodynamic forces on your rocket act. So by adding bigger and bigger fins, you move your center of pressure kind of over here. So now if your rocket kind of tilts, so it's not going straight anymore, you'll get a force acting right here that'll make the rocket stay straight. Because it'll pivot around here and you'll have a force that acts this way. So the fins act to stabilize the rocket. By making bigger fins, you move your center of pressure back here. Smaller fins, you move your center of pressure here. Based on where your center of pressure is, your rocket is more or less stable. Too stable is sometimes a bad thing, because then if there's a bit of wind, it follows the wind and does this. Unstable is obviously a bad thing, because now the fins can't correct your rocket's motion and it crashes. So there's kind of a balance that we've had trouble with in the past of finding that between too stable and unstable. But that's how fins work. So that's the only way we stabilize a rocket. Problem is fins only work when there's an atmosphere. In the vacuum, once you get high enough, fins don't stabilize your rocket anymore. So once we start getting to space, a lot of teams use spin stabilization, which is where you spin your rocket very fast. And once it's spinning very fast, it doesn't want to tilt just because it's like that gyroscope. I'm not sure if any of you guys have seen those like bicycle demonstrations where you spin up a bicycle wheel and then it kind of floats into air. So that's what rockets use a lot. But you know, spinning too fast brings its own problems. When you're spinning too fast, your parachute comes out and then wraps around your rocket, right? There's issues. Yeah.
How do you get the rocket to actually spin?
Yeah, so
It's only got one engine. You can't really produce a torque, just one engine.
yeah, so rockets will spin no matter what you do because the fins will never be perfectly straight. So if the fins are a little tilted or off, the rocket will start spinning. Our rocket was actually pretty good. Surprisingly, our fins were pretty straight. It wasn't spinning that fast, but if you wanted to, we could adjust that. Some teams adjust the tilt, some teams just be like, oh, it'll spin. So there's ways to calculate your spin, but always when you're messing with these things, you can overdo it. You can spin your rocket too fast, you can start wobbling. So, you know, it's always a fine balance.
All right.
Yeah, but that's our plan. So a combination of fin stabilization and spin stabilization for our space shot. Yeah. Anyone have any questions about any of that? Okay.
What?
Yeah.
Have you guys considered cold gas thrusters?
No. Well, we have, but it's just too much work. Fins work fine. You know, for people who don't know, cold gas thrusters is where you just use like spray gas out of your rocket, like you high pressure gas and it tilts your rocket or adjusts your rocket. You know, we're a small team, 40 people. It's hard to test that stuff. Yeah, it would violate ITAR. It's less violating than like TVC. Like you'll see more teams willing to risk flying it. I know people do it on like tiny rockets for fun. They'll use like a CO2 cylinder about this big and then try things like that, cold gas thrusters. But you know, we don't really want to mess with active controls. We're walking a fine line as it is as a liquid rocketry team going to space. So, you know, yeah.
Yeah, I was gonna ask.
Yeah. Okay.
Yeah, control wheel.
Okay. Yeah, so he said, yeah, the Kate system comes with an altitude unlocked GPS, so that means it'll even work past that limit on altitude. So the law technically says you can't go this fast and this high, but a lot of GPSs, or you can't go this fast or this high. A lot of GPSs will take 1 into account. It's complicated. But yeah, there's some GPSs that we can use that'll work. So yeah, manufacturing, we have all these parts. We know we want them to work. We want to manufacture them now, right? Like manufacturing is hard. It's probably the hardest thing we do. Just because it's hard, you start with a block of aluminum or a block of metal or whatever wood, plastic, try to make that a final part. It's hard. We want to simplify that process as much as possible so we can focus on rocketry instead of making parts. So the way that works on our team is we focus on creating 2D assemblies for easy manufacturing. 2D is easy, right? You put it on a laser cutter, it draws out your part, you're done. You put it on a water jet, draws out your part, you're done. We can get up to like 4-inch tall. I think the most we've done is like 3.5-inch tall parts on a water jet. So you can get some pretty beefy parts on a water jet as long as they're 2D. If we do have to go with 3D geometries, we simplify those as much as possible. We make sure that those are easy to manufacture, don't take too many operations, don't need too high precision. And part of that process is manufacturing communication. So, you know, I'm the propulsion lead. I may not work super closely with the machine shop all the time. Our manufacturing lead, he knows a lot more about the machine shop, or he has the bandwidth to go to the machine shop and ask them questions. I'll work with them. So there's a lot of communication between the teams to figure out how we can optimize parts for manufacturability and get them built as soon as we can. Primary sources for machining, Jacobs. So if you have a maker pass, you can machine at the Jacobs makerspace. They have a makerspace upstairs. They have a metal shop downstairs with a water jet laser cutter metal tools.
You get a maker pass or
All our club maker passes are allotted already. So we only get 10 discounted maker passes per club each year. Those were all assigned last year. Yeah. Next year you can ask for one. It's kind of on a first come, first serve quasi, like how much work are you willing to put in basis. So yeah,
With the maker pass, you can still get one. It's just, you won't get the discount.
yeah, 125.
Yeah. Although it- it's like half for some financial aid and then full for certain
it's
others.
just for the semester, it's not the whole.
Yeah. Yeah, just for the semester, and it gives you access to everything. You do have to do training, so if any of you guys want a maker pass, I'd encourage you to get it right now, start training, because they end the training slots in a few weeks, and once there are no more training slots, you can't use all the cool tools. You're stuck with the lame stuff. Yeah, it's a big waste of money, so
I have a maker's pass, what tools should I get the trainings for?
yeah, metal shop, Fab Light and water jet.
Not like water.
Yeah,
I think I already did the back light one, I just got it.
yeah, so those two, Fab Light and water jet, they're most powerful.
Yeah, I'm thinking E29, so
Mhm.
I get access to the activating shop as well.
Mhm.
Will I get the training for the water jet for that?
No, yeah. So if any of you guys are taking E29, is anyone taking E29? Is anyone taking 102B? Anyone taking ME 103? There's some more classes, but if you guys are taking those classes, do the machine shop training. Your professors will say it's open, do it right now. Because once you're not in those classes, you can't get machine shop training. The slots fill up. So even if you never intend to machine a part again, do the training right now. It takes 4 or 5 hours, a single day of your life. And then if you ever decide you want to go machining, you always have access to the machine shop. So make sure you get that machining. A lot of people take those classes, they never get the machine shop training, and then they're screwed for the rest of their like Berkeley career. You know, it's hard to get that training in the mechanical engineering machine shop if you're not taking those classes. I'm not sure how it works for grad students. Yeah. But yeah, if you're undergrad, there's some more classes that you can take, but I'd encourage you guys to get machine shop training and the maker pass if you want to manufacture parts and make those parts. If you don't want to, that's okay too. But I'd encourage you guys to. Yeah, molds, fixtures for composites. So not everything is made out of metal. Not everything can be made on a water jet or on a mill. We do a lot of work with composite material. So composite material is something made out of multiple materials. For us, that's carbon fiber and fiberglass. So the way these materials work is you have like a cloth made out of glass fibers, or you have carbon fibers. You soak them in epoxy, and that makes a very rigid structure. Kind of the fibers provide a lot of the strength and the pulling, just because if you imagine a piece of rope, it's very hard to break. And then those are interleaved, and then you add an epoxy that holds those into a certain orientation. And the total material property is very stiff, very resistant to a lot of forces. But there are concerns with that, right? It's a complicated material to work with. You need molds, you need things to set that up. I'm not the expert on on composites. If you talk to Asa Garner, our structures lead, he knows way more about composites and the process for doing that, if you guys are interested in that. And the overall benefit for composites is they're generally lighter for the same stiffness compared to other materials. Yeah, anyone have any questions about this design for manufacturability stuff? No? Okay. So assembling the system, once we have all the parts in hand, we have to assemble the system. We work at a Richmond Field Station. At Richmond Field Station, we have a few tools. They're kind of crappy. They're not the best, but it gets the job done. Richmond Field Station has the tendency to destroy our tools. It's located maybe like 200, 300 meters from water, or maybe half a mile from water. So that salt water really messes with our tools. The air is salty, things start rusting. So that kind of makes our tools kind of crappy, but they're good enough for there, and it's not currently worth the investment to buy really nice tools that will just get destroyed over time. So we're kind of in that intermediate phase. We're running into a decent more money. So you may see tool upgrades happen over the course of this semester and next semester. So we do have a decent number of tools at RFS, but if we need more advanced things, we machine them in-house here. Yeah, so we assemble support structures. Once we're done with all the plumbing, we need things to hold it all together. We assemble support structures to hold up our system and test it. So you can see here, this was the original frame for the cart, and it turned into this cart with all the tanks, everything we need, all the plumbing. Same thing here, we have the structure to hold up our tanks and stuff in a vertical orientation. Yeah. So we have a safety training video. I'm not sure where it was posted, if it was posted in Ignition, but we're in Ignition. Okay, so one of our members put together a great video guide, and there's like a short quiz that you should take. just so we know that you're gonna use the tool safely. Also, if you guys haven't signed the waiver, sign the waiver. That's important for our liability. Okay. So once we built up our systems, we filled them up, we've ran a test, something will go wrong. Inevitably, every time we've done something, even if we want, like, there's always something go wrong, right? And we don't know what goes wrong just by looking at it. It might look fine and things might go crazy on the internals. So with all of our avionics stuff, all of our temperature sensors, all of our pressure sensors, all of our load cells, which measure like how much load they're experiencing or how much thrust, all of our fill level sensing, which figures out how full our tanks are. All of these sensors come together, give us a lot of data that we can then analyze and improve the performance or improve things that went wrong the next time. So one of the great things about our team is we have the most powerful avionics suite of almost any collegiate rocketry team at the undergrad level. We collect a lot of data, we display the data very nicely. Nolan runs a lot of scripts on the data. He works with the simulations team to analyze that data very quickly so we can do a test, immediately get results and optimize our feeds and pressures and things like that and redo a test. So yeah, that's all in Python and MATLAB. So, you know, if you're interested in data science, CS side of things, that might be useful. That might be something you're interested in, or not, if you're not interested in doing more coding after you get done with class. But yeah, so Python and MATLAB based, and it enables comparisons between simulation and actual test data, right? So as we said, we're always trying to make those simulations match reality and make the reality match the simulations. So you can see here, this is a simulation that performed really well at the beginning. So you can see how this pressure, the data matched the simulation really, really well. And then once we ran out of propellant, probably around the 12-second point, it stopped. But you know, that's when we ran out of propellant, right? So for most of the time, this simulation worked perfectly. So that's a great result. We want to keep replicating this every time. Maybe here, I think this is, we ran out of fuel maybe a little earlier than simulated. Is that what it represents? Yeah, okay, okay.
It's rarely ever this good though, it's like.
Okay.
Or like a
Overfitted. Yeah, okay. But this is the goal, right? We're trying to make it match perfectly. A lot of times that creates these massive plots, right? Like 4-dimensional, 5-dimensional, like whatever dimensional plots that we're trying to look at and analyze. So, you know, you have a lot of parameters that go into it, and then we try to get a result that explains how our engine will perform or how our rocket will perform. So we're going to look at this graph, try to figure out what point on this graph do we want to hit? Do we want to get like this point? Do we want to get this point? What'll get us our best results? Yeah.
How do you read a plot like that?
Yeah, so you have your 3 axes, and then you have kind of, this would be like your overall performance. So if you want to know your performance at this OF ratio, this TMFR, this throat diameter.
It's one out, like the 3 inputs are the axes and the color is the.
Yeah.
Alright.
TMFR is total mass flow rate. So total propellant is going into the engine, right?
So yeah, this is all engine impulse, so essentially the efficiency we're getting at. And it's dependent on flow rates, which is the TMFR, total mass flow rate. OF is your propellant ratio. Throat diameter is the throat of your nozzle, how large that gets.
Yes.
Yeah, like when we're trying to predict how things behave, like there's 2 kind of ways to do it. Like one way is like using actual physics equations and just like plugging in the input and stuff. Sometimes like the process is just so complex that like, you know, like it's just like not worth using a bunch of equations. So what we do instead of just collect a bunch of data and then create a plot like this, where like instead of being based off like a specific equation, it's just like creating like a massive lookup table based off of a bunch of data we're collecting and having all that data allows us to create like straight out of.
Yeah. So there's like a combination of like theoretical based and numerical based and empirical based simulation. Yeah. Okay, so once we analyze all of that data, we can throw it all together.
Wait, so to generate this graph, you made a bunch of models and you can that.
This one's a different.
This was actually generated through third-party software. So this is not an empirical fit. This is all simulated data on combustion using a third-party software called RPA, Rocket Propulsion Analysis. And you know, this is all just automated through RPA, and then we export to MATLAB and make nice colorful plots.
There's similar plots for like, for example, our mechanical that we used to use. It's like there's like the input pressure that you give it. There's like the pressure on one side of it, and there's like the flow rate going through it. It's like we don't know like how to model that exactly, so we'll just like run a bunch of like quick tests. Yeah, collect a bunch of data points of like across a wide range of like those different inputs, like what pressure we're setting it to, the pressure upstream, and then like how fast it's going through there. Then we get like a plot like that, like we use right here, and that just is like the characterization. And we just to predict the future, like in the future, we want to predict how the regulators can behave. We just go like feed in the inputs and then based off like all those fly like the closest out.
So, you did this rate, all your graphs, you're the one that talked about graphs from RPA.
No, so,
It's a mix.
yes,
And then the one to the far left is your simulation, right? For your code.
no. Bottom left, okay, so this is actual data. So this is our thrust data. So one is load cell one is load cell two. We add them to get the total thrust. The blue line is from simulation. The orange line is from actual thrust. This one is RPA. So once RPA generates a plot, then we can put that as a lookup table in our simulation. So when we get pressures and things in our simulation, we'll say, let's say our engine total mass flow rate is like 1.5. We plug that in to our own simulation. We see what our actual engine performed at a TMF R of 1.5, and we use this lookup table, match those parameters so we can see our engine efficiency, because RPA assumes a certain efficiency, and we can see how close we are to that efficiency by comparing RPA versus our actual results. So RPA, it does a lot of the combustion analysis, things like that. So by using this lookup table, we don't have to implement it ourselves.
The other blocks you saw, where are they?
These ones?
Yeah, so those are generated from actual data that we've collected. So the plane there, that's like one discrete measurement, if you could see those little blue points there, per test essentially, and then the much larger array is maybe taking thousands of data samples throughout the duration of a flow, where we're getting one data point per hundredth of a second.
Good. So data analysis happens once we do enough cold flow. So there's testing campaign starts with water flows. We flow water through our system. Then we go to cold flows. We flow liquid nitrogen through our system. Then we hot fire, which is where you flow liquid oxygen propane through our system and light that thing like a candle. So it's a long testing campaign. And once we're done with that testing campaign, once we've gone through all the steps, we figured out this is as good as it's going to get, we go to hot fire. So hot fire is really the only case we can measure a lot of things. We can measure mixing efficiency on some level just through our thrust. We can measure like how well everything matches simulations. So yeah, it's a long testing campaign. These are cold flows. You can see liquid nitrogen creates all this condensation in the air. Hot fire on hot form, and then vertical hot fire and launch. So it's a many-step process, constantly revising things and improving them. Okay. So going into the very specifics of propulsion, let's talk about the engine. This engine was designed a few years ago, and we've kind of stuck with the engine. We're currently working on some things to make some mild changes to the engine, maybe improve performance, maybe help increase burn duration. But this engine was designed for a certain set of conditions, and we've been operating with this engine ever since. Once you have an engine, you're kind of locked into that engine just because you don't want to risk changing it because it's a massive testing campaign, and you never know if the next one will work. So there are three main sections: injector, combustion chamber, nozzle. The injector is this thing over here. The injector injects the fuel into the engine, make sure they're well mixed, make sure that they're mixed in the right ratios, things like that. The combustion chamber is like this whole tube. Tube helps to facilitate the burn. If you have a longer tube, you get more burning inside the tube. If you have a shorter tube, it's not burned, but then you get mass benefit, things like that. The nozzle is over here, so that kind of accelerates the flow, directs the flow out of your engine, shoots it out the back. Rocket efficiency is all about how fast you can get the propellants at the back, and the nozzle speeds up that combustion process, redirects it all in the same direction. Because if you can imagine in here, it's all a bunch of tiny explosions, kind of randomly, that nozzle really directs that flow down. The injector, it's like down, kind of, then the nozzle really concentrates that, shoots it up the bottom. So assembly notes, we use snap rings to assemble. You don't really need to know the exact, it'll be easier to show in person. Sealed with O-rings. O-rings are just like rubber rings. You'll see them on water bottles, things like that. They seal when you apply pressure between two things. Yeah, so our engine uses an ablative. What an ablative is it's something that ablates away, which means it burns away. As it burns away, it takes heat from the engine or heat from the combustion outside of the engine, and it protects the walls of our engine. So over here, we have this aluminum. In here, we have ablative, and that absorbs heat. And here we have a nozzle, and that nozzle is made out of graphite. Because the nozzle gets the hottest and graphite can withstand really high temperatures. Yeah.
For the ablative material, would you have to replace it after every single
Yeah.
time you fire the engine?
Yeah, so we replace it.
My follow-up question is, do you remove the nozzle or do you remove the injector? How do you replace it?
Yeah, so everything's yeah.
Yeah, the whole thing from the part, it's like.
Modular design.
Yeah. Yeah. Yeah,
Was the nozzle shape chosen because of machining constraints or your simulation to pull out like economic model?
yeah, so the way it works is like with RPA, or all your parameters, there is a most optimal nozzle. We cannot machine that, and actually we're limited to like what we can buy online. So we buy a nozzle that's actually designed for a solid rocket motor. That's machined in some cases to fit to be more optimal. But you know, we're not operating with this nice curvy shape. Just because one thing about machining these graphite nozzles or phenolic nozzles, which is where we have an ablative nozzle, those materials, phenolic causes cancer, like the gut. Everything in rocketry causes cancer on some level. Phenolic causes cancer. Yeah. So it gets in the air. You can't machine that. Like no machine shop will let you touch that. You have to do it yourself or whatever. So we can't do that. Graphite, it damages tool machine. The dust gets in everything, damages things. So we're kind of limited to what we can do. We used to be able to do some of this stuff in the physics machine shop. When we had a student on our team who worked there and had a really close relationship with the physics machine shop lead. She graduated, so we don't have that connection to the physics machine shop. Now we're stuck with like the tools everyone else uses, so we really can't do any of this stuff in here. So we're outsourcing some of the work to external companies that can machine these things for us. I don't know, maybe that'll offer, maybe now that we fully have to commit to going externally, maybe we can get optimal nozzle geometry, who knows? But that's something we've had to run into this semester, and it's an issue leading up to the spot fire that we're thinking about right now.
You're not buy like no that's just kind of like a lower,
No, they won't. We've asked them. They're not going to let us bring it anywhere into the machine shop. We've thought about buying our own lathe, but you know, it's a big investment. We could do it with maybe like a Harbor Freight really bad mini lathe, but it's like a can of worms. And back when we had that physics machine shop resource, it was like just easier to do that there. But now we're thinking about it. And really you can't get the optimal nozzle geometry without a CNC lathe, just because this curve is really hard to do by hand. So it's something we're thinking about right now.
Yeah, like this whole thing is kind of designed around that also.
Yeah, like we found a nozzle we could buy and then we designed an engine around that nozzle.
Like if you're like printing, for example, then you could go like, you don't want, you start from somewhere else and you just say like, what for us, like you're not constrained by that. You don't.
Yeah, it's not bad though, like conical versus a bell nozzle is not too really different number.
It's like 93 versus like 90.
Yeah.
Oh, I am almost out of time. Okay. I have 10 minutes left, I think. Oh, okay. Yeah. I'm sure all of these people will stay, or maybe some of you guys will stay.
Okay, cool. It could be a 10 or 30-minute session.
Okay, so our injector, again, this is really complicated, but this mixes our propellants. We have a pintle injector. A pintle is just like a way of there are different types of things, different types of ways of shooting the fuel into the engine and shooting the LOX or liquid oxygen into the engine so they mix. Pintle is one way. It just describes the geometry. The way a pintle works is you have this thing, it's like a cap, the liquid oxygen flows into it, you have a bunch of holes on the side like this. The liquid oxygen shoots out these holes. Then you have propane that shoots up like this. So the propane shoots up like this, those two intersect right here, they mix, they form a cone. That's a really well mixed propane and liquid oxygen mixture, and then that burns. But there are a lot of other ways to do it. There's things called impinging jets. So you might shoot like your propane this way, shoot your oxygen this way, and then it creates like a jet like this. So there are a lot of options. We put the pintle for machinability. Also, pintles are a bit easier in terms of combustion stability, which is something we were somewhat worried or might be a concern. So pintle has a lot of advantages, but a lot of disadvantages, just like any other injector. So, you know, choosing the injector is a big part of the engine design. Yeah.
Is the pintle active?
No. Yeah, so we don't actuate our engine pintle just because we never intended to throttle. Yeah, it doesn't retreat back to cut off fuel flow or anything. We have valves for that.
So you're just like going like your maximum flow rate.
Yeah. So for E3, since the atmosphere, so in a lot of rockets, you may want to throttle your engine because as you go through the atmosphere, there's drag. There's drag as you get through the thinner parts, there's less drag. So you can find this optimal curve of when to blast your engine, when to lay back to get the most altitude with the fuel you have. But for E3 or E1, which is only going to at most 25,000 feet, The atmosphere is relatively constant density. It doesn't make sense to have a throttleable engine, so you make our engine as powerful as it can be and then send it up. Yeah, so there's a lot of stuff going on in there. It's easier to explain in person, but that's kind of the high level overview. The liquid oxygen flows through here, comes out, propane flows through here, comes out.
Something interesting, like we actually found a problem with our people.
Yeah.
Yesterday through by doing CFD, then we realized like, like the velocity out of all holes is not at all distributed. So like it's going way faster out of those bottom holes than it should be, and that's causing like a problem that we've just been experiencing and didn't really know the source of. So
Yeah. Oh,
I mean, it's just because like there's two rows of holes and the row on the bottom is like, I mean, it makes sense in hindsight, like it's getting way more flow through just because the top.
Oh, sorry, bottom, you meant like.
Oh, yeah.
Oh, yeah.
So one of those cats.
Yeah, so we're currently trying to figure out our pintle. Like this might be better. So one thing is like maybe a impure. I'm not sure how well this describes the phenomena, but once that propane hits the first set of holes, it's like already directed. And since the second set of holes, and like just because of the way the pintle works on the inside, there's a lot of fuel coming out the top hole, so it's not even flow. So we're gonna try CFD on things like changing the hole sizes, adjusting things, but obviously there's always a limit with the manufacturability. You can only make these holes so small before you can't drill that hole size anymore. So that's something we're talking about.
So small that we can like sort of just adapt it.
Yeah.
And then do a like finish counters.
Yeah. So yeah, now 3D printing, metal 3D printing is like cheap enough where we could get this pintle for maybe 15-20 bucks. And you know, when machine time takes like half an hour to an hour, it's like maybe we should 3D print it.
You're trying a bigger set of tools.
Yeah. Yeah, kind of even out the flow rate through them, even out not the flow rate, realize the momentum, which is I guess the flow rate, very heavily correlated with the flow rate.
Those upper holes did already exist. We're just enlarging the upper holes sort of at the expense of the lower holes. Treating the bottom ones. So
yeah,
that out.
So this is our current pintle. You can see all the holes are the same size here. So adjusting the hole sizes but maintaining the same area will hopefully give us the same total mass flow rate, but in a more optimal way, so you get better ablation, which I can show on the next slide. Why that's important. So we have this aluminum chamber that's around our engine. We have an outer liner of phenolic, so that's the ablative part I was talking about that burns away. So we have these liners, we have our nozzle. So here you can see the star-shaped pattern, and that's kind of what Nolan was hinting at. We think that this pintle with the uneven flow through all of the holes is causing extra liquid oxygen to hit the side of the walls, and there's like a 12-star pattern. And what do you know? We have 12 holes in our pintle. So that was a big thing, right? I didn't talk about this, but we have 12 holes in our diffuser plate. We have 12 holes in our pintle. We've tried changing the diffuser plate a bunch of times. It's not really showing any improvement. And now maybe it's a pintle. So, you know, with liquid rocketry, there's a lot of things. So maybe we should choose different numbers for different things. You know, choose prime numbers so nothing lines up. Oh, no. But basically, it's a big mystery. Sometimes when this stuff's burning, right, you can't just measure the flow rates. You can't just see. You can only do like post-investigatory analysis. And sometimes it takes a lot of hot fires to figure this out. We've done 14 hot fires, figured it out with sims a few days ago, or last night. Ideally, we figure that out earlier as we get better at sims. Hopefully that's something we can do. Each semester. So it seems like we've maintained a pretty rapid pace of 2 FAR dates per year. Each FAR date we plan for 3 burns. Usually that goes down to 2 or 3. Or sorry, usually that goes from 3 to 2 realistically. Depends on when we go. In February, it gets dark at 5. In May, it gets dark at 9, 8 or 9, so we can hot fire longer. Things like that.
Like 5. That's the limit.
Yeah, so 5 burns a semester is kind of the goal. Yeah.
This is like a cool question, but you have like 2 different views, 2 different weapon chamber and nozzle.
Mhm.
You run into like sealing issues, just like different extensions.
Yeah, so this part, the injector is stainless steel and the chamber is aluminum. It's only the bottom plate is stainless steel. Yeah. I think one thing is just that the outer liner doesn't get that warm. Even during hot fires, we've measured the temperature of the outer wall. It doesn't get too hot where that would be an issue. Yeah, hopefully, because also this doesn't heat up too much just because it's cooled from the back with the propane. And also the flame front is kind of up here. So I'm not actually sure what the temperature of this is because it's pretty hard to measure. But if it were expanding quite significantly, it would just seal better. And O-rings generally have a lot of give kind of on the scale, like this scale, they're not expanding too much. So even if we're kind of at the limits, in theory, those O-rings might still be within their margins of sealing. Yeah. Yeah, we do tests called hydro testing, which is where we fill up our engine with water, pressurize that, and make sure that all these seals still happen. Just because when it's burning, that's basically a bunch of pressure inside the engine. Yeah, let me speed up. It seems like we're running into structure side. Okay. So basically, yeah, we have our pressure tank. It pushes that fuel out of our oxidizer and fuel tank into our engine. So that's this tank up here. It pushes fuel and liquid oxygen out of these two tanks into our engine down here. Pressure is carefully controlled through regulators. Before we had these mechanical regulators, were kind of bad. We had this, you know, as we said, this massive best fit curve trying to analyze those mechanical regulators, figure out how they'll perform in different conditions, make those work. There's a lot of work. We've switched to electronic regulators. Woo! And electronic regulators are better just because they're a lot cheaper. So it's around $100 per regulator. All built kind of combination of off-the-shelf components, we machine at here, versus $700 for real regulators. They're electronic, which means we can measure pressures, we can adjust them on the fly. We make sure they get much flatter curves. So it's gone through a lot of iterations. It's hot fired. It's mechanically very simple, just a motor attached to a valve. And it can maintain pressures pretty accurately compared to our mechanical regulators. So this is actually very optimal performance. We don't get the performance during a burn. This is with testing with water. But yeah, it opens up a lot of possibilities. The next steps on how to get started on propulsion work. So we have guides on cold flow safety, hot fire safety, and general safety resources. So that's especially being updated this semester. Maddie will focus on that just because we're starting to deal with more dangerous things, bigger pressures, bigger engines. As we go forward, that'll become more important. So make sure you guys watch these videos. Even if you'll only ever be standing 30 feet away from a cold flow, it's still important to know safety just for the safety of others and to be aware of the entire system. Another great thing about our team is everyone gets a chance to touch the scary stuff. You can interact with things that are very dangerous on a day-to-day basis and not even know they're dangerous. So making sure to have a very solid understanding of safety, always paying attention to what more experienced members of the team have to say about safety, being spatially aware is very important when we're dealing with very high pressure things, very cold things, very hot things, high voltage systems, stuff like that. So trainings, to make sure you guys are trained, we do have a Sunday training this weekend. That's mandatory. If you can't come on Sunday, we can do a training slot some other time or kind of in separate training thing for you, but try to make it out on Sunday. The details are posted, I think, already on Slack signups, right? Also, these EHS has trainings that you guys should take. So all of this stuff is very useful, and you must complete the RFS safety training to have access to RFS. So tiny URL, it'll go to here. Berkeley wants us to take this course. The TLDR of this is that Richmond Field Station is at a decommissioned chemical site. There is a lot of arsenic in the ground, more than arsenic in the ground, stuff we don't even know. In theory, someone said there's like a radioactive barrel buried at RFS.
It's not RFS, it's like near.
Okay.
Those are very active.
Well, it's like basically RFS.
It's like not, but it's like.
But the good thing is that it's in a barrel and it's below the earth, so it's like really not.
Yeah, so basically like the safety guidelines say don't dig. If you see a plant growing with some nice delicious berries on it, those berries have arsenic in them, don't eat the berries. I don't know how the turkeys survive off of RFS.
You'll be fine. Yeah,
you'll be fine. It's generally safe. The EPA has done many tests of this area. It's not a risk to be out and about walking around. But it is a risk if you dig deep beneath the soil where kind of those contaminants are, or kind of disturb things, but that's not really a big issue for us. Yeah, other safety things, we deal with composites. Those get into the air, mess up your lungs, give you lung cancer, kind of like asbestos, fiberglass, carbon fiber, all of those things are bad for you, but they're great for rockets. So there's a lot of safety concerns, and we kind of go over that over the course of the semester, so be safety aware. Yeah.
Another thing to note, there's a liability waiver, so please sign that.
Yeah, someone in chat. Yeah, just don't eat the soil. I mean, kind of obvious. Yeah, what were you gonna ask?
I was gonna ask you
Yeah, it'll be posted in Slack in the ignition channel.
find it.
Oh.
You want to show how to browse channels?
Yeah, so if you go here. What?
After you're done.
Okay, are you in any of the channels?
Yeah,
What channels are you in?
I am in.
Okay.
Announcements,
Okay, well, there's a lot more. Yeah, okay. Just so if you go to the channel thing on it might be, I'm not sure how to do it on mobile. But if you hit the plus button, it'll show you all of them. Yeah, so I join definitely, of course, announcements, engine. Yeah, join everything.
Eventually, we don't wanna.
Yeah, yeah. It's all useful. Things may be more inactive, like the newsletter is more active when we're about to release a newsletter. But join all the channels just so you're aware of everything, even if you never read the avionics channel. Just join it. You can start channels. You can't really reorder them, it's all alphabetical, but you can start channels that you find more important. And I'd recommend you do that. Yeah.
You mentioned there were two camps, you could read, so the region.
Mhm.
Is there a
No, so Nolan is working really, so for people who don't know, regenerative cooling is when you pump fuel through your engine because that fuel is cold or cold relative to the flame of combustion. So you pump fuel through your engine and then back into your engine to burn it. And by flowing it around your engine, you keep your engine cool so your engine doesn't melt. And that's opposed to ablative where it burns away to protect your engine. So those are the two things we're heading towards as we work on our space shot. There's no internal deadline. I think it really depends on our test campaign. So Nolan's really heavily doing the simulations for regenerative. ASA has plans to test a homemade ablative engine, which is something we need to do for an E3. So we're kind of still developing those in parallel on some small scales before we can fully commit to one or the other.
It's too early to tell, it's like moving towards both of them right now until like. There's like something that's like clearly to do one or the other.
It depends on whether we can manufacture one or the other. Right, they both have like very well defined advantages and disadvantages, and very little overlap, other than the fact that they're both rocket engines.
Yeah.
Yes, there are tentative designs like floating around for regen, for ablative, and right now we're just trying to figure out, are these manufacturable? Do these meet our requirements in terms of thrust and performance?
So yeah, kind of the general gist of how it'll work if you join the propulsion team. We have our general meetings on Monday. Propulsion meetings on propulsion and structures are one big meeting on Tuesday. Avionics is on Wednesday. We do have CAD work sessions spaced out throughout the week. So ASA or I will host these where we'll say, okay, guys, let's all come together and work on one thing, or let's all just sit together in a room and work on things. So you can feel free to join those on a day-to-day basis whenever. Those are kind of announced last minute whenever people have time, or there'll be when-to meets for that stuff. So yeah, we try to keep everyone in the loop. Come out to our Saturday work sessions as often as you can. Every week is the goal. Yeah, so that's the gist of propulsion. Yeah. Yeah. So the weekly meeting, like the work sessions, are at Richmond Field Station, which is about a 20-minute drive away. We carpool. All the other meetings will be on campus. Our general meetings are in Jacobs. The basement of Jacobs. Our propulsion meetings are either here or Dwinell. It's kind of across campus, but it depends on where Ace and I are on campus, and we just pick the one closest to us. I'd aim for probably Corey. They seem to be trending towards Corey. Avionics is always in Corey Wednesdays. Okay. Yeah, all our meetings are at 7 o'clock nominally. They have been changing over the last week and this week just because all these ignition sessions are kind of during our meeting time. Next week it should settle down. But if we do want to go to our Richmond Field Station on a weekday, maybe we'll shift a meeting or adjust things around. But Tuesday, 7 o'clock. Yeah. We do announce it on every week. We announce it and host a Zoom pretty consistently. Yeah. I'd encourage you guys to come in person though. It's much more valuable in person. It's hard to engage over Zoom. What?
More fun.
Yeah, it's definitely more fun. Okay. Any other questions? No, okay. I will pass it off to Asa for structures.
Sweet. Yes, so you feel like a medium short.
No, I don't want to.
So I guess
Yeah.
recording would have.
Yeah. I'm gonna stop the recording. For people on Zoom, join Asa's Zoom.